In this module, we will focus on clocks. In this module, let's identify what is a clock, how a clock is defined, what is the clock period, pulse width, duty cycle, and all the different properties of a clock. We'll also look at how the clock is propagated in a design. Clocks are periodic signals that are broadcast and therefore are generated either on the chip or outside of the chip. A crystal oscillator can be used to generate clocks outside of a chip, and to generate it within the chip, you use phase-locked loops or PLLs. In digital circuits, clocks play a vital role because they trigger the storage of these memory devices, and they control your state machines. If you have flops or latches in your design, you're using a clock to trigger the storage of data into those flops and latches. In Verilog language, anytime you see an always at posedge clock or always at negedge clock or always at clock, you're creating a storage device. If a posedge clock is capturing the data into the storage device, then that device is a positive edge triggered flop. Similarly, the negedge clock stores data into a negative edge triggered flop. Each clock period has one positive edge and one negative edge. New data can arrive at each capturing clock edge. Therefore, the clock period determines what time constraint a flop has, in order to safely store the data before the next data arrives. Your design might have different kinds of flops and latches that use different clock edges to trigger the storage of data into the flop or latch. Therefore, it is helpful to idealize the clocks, whenever you are unsure of whether the triggering edge is a rising edge or a falling edge. It depends on the type of device on how clock is used. Therefore, you can idealize the clock with the leading edge as the initial edge, and the trailing edge as the following edge. In the graphic below, CLK1 shows a leading edge at 0 and it may be a rising or a falling edge. At the time unit 2, you have a trailing edge, and that could either be a rising or a falling edge, depending on how the clock is configured. You can use these ideal clocks for the purposes of our analyses whenever we are unsure of the clock properties. The clock has multiple properties. One of them being the clock period, which defines at what interval the waveform repeats itself, and then you have the rising edges and the falling edges. The rising edge is when the clock is going from low to high, the falling edge is when the clock is going from high to low. The pulse width is determined based on how much the clock is high. When you associate those ideal clocks with an actual port, if the port is driving only positive edge triggered flops, then a rising edge can be set for the initial leading edge of the clock, and if the port is driving negative edge triggered flops, then a falling edge can be the leading edge. If you have a mixed bag of positive and negative edge triggered flops in your design, it is best to define separate clocks for the two types of flops. Otherwise, it requires a very careful analysis of the various launch and capture edges of the clock to determine proper storage of data into the flops. In some designs, it is important to understand duty cycle because when there is a transfer of data from positive edge triggered to negative edge triggered flops or vice versa, there is the reliance on duty cycle. This is also important in the case of a latch. Whether the latch is transparent or opaque is determined by the duty cycle. In most designs, where there are just positive edge triggered flops or just negative edge triggered flops, the duty cycle doesn't play much of a role. Let us look at the following examples. Here, a clock is defined by its period of 4 and the edges of 0 and 2. Duty cycle is calculated as pulse width high divided by clock period, as shown in the top waveform, which is 2-0 divided by 4. Therefore, we have a 50% duty cycle. On the bottom waveform the edges are defined at 0 and 1. Therefore, the pulse width is high only for 1 unit, and so it's a 25% duty cycle. Take a minute to do this activity, to improve your understanding. In any design, a clock triggers several flops and latches. These clocks are considered high fan-out nets, and they need to reach or traverse the entire design to reach these flops and latches. To keep the integrity of the clock signal, it needs to be constantly buffered, and these buffers can be in different structures. The most common forms are known as clock trees or clock meshes, and so you would see different types of buffers along the clock tree and/or clock mesh. These are generally referred to as clock trees. You might start out with a drive booster and a bunch of repeaters, then different kinds of buffer strengths placed along the length of the tree traverses to reach the flops or latches. In the case where your design does not have any clocks typically during synthesis, the clock tree doesn't exist, so you need to mark the effect of a clock tree into your design. At this stage, during synthesis, it's known as the ideal mode. When the clock buffers are inserted into the design, it is known as the propagated mode, where the modeling that we have done is replaced with the actual clock information. As we've seen before, the transition time is the time taken by a signal to change states. In the case of a clock, this is known as the clock slew, and clock slew is essential in ideal mode. We need to define the clock slew in ideal mode because ideal clocks typically don't have any rise and fall times, it's instantaneous. Whereas once the clocks are inserted, then the STA tools will calculate the slews of the clocks through the buffers that are inserted. Because we're talking about real clocks, these clocks are generated by clock oscillators or PLLs. There is an uncertainty in the period and the duty cycle of the clock, because of the circuitry that is generating these clocks. This is considered as clock jitter. Each clock oscillator comes with a datasheet, in which the clock jitter is listed. Your clock also has a slight variance in the clock arrivals at different leaf flops in the design, because of the clock trees and buffers in your clock path. Ideally, these clock trees are modeled to reduce variance of the clock arrival at the different leaf flops, but it is inevitable because it is a real design where data transfers between flops happen across various flops in the design. This variance in clock arrival times due to the clock trees is called clock skew. Clock uncertainty can be thought of as a combination of clock skew and clock jitter. The STA tools report clock uncertainty as calculated for all the different clocks in your design. You can use clock uncertainty to add pessimism to your design, especially for paths that start from one clock to another. You need to model the clock arrival times at different flops and latches in your design to determine the required time for that signal to reach the flop. Clock arrival times are modeled via clock latencies. You need to define two types of latencies, source latency and network latency. Source latency is measured up to the point of entry of the clock into the design or block. Network latency is measured inside the design. So, any buffering that you do inside of your design, is included in the network latency. The total latency at any given flop or a latch, is therefore the combination of source latency and network latency. In ideal mode, you model the effect of clock buffers using these clock latencies. In propagated mode, you can remove network latency. Clock latencies are commonly referred to as insertion delays. Take a minute to do this activity, to improve your understanding. When a signal moves from one flop to another, the signal is considered launched from one flop and captured on another flop. The clock that launches the data is called the launch clock and the edge of the clock that launches that data is called the launch edge. The capture clock is the one that captures the data and the edge that captures that data is called the capture edge. In this design, there is only one clock that is both launching the data on one rising edge and capturing the data at a different rising edge. In this case, the difference between the capture edge and launch edge is one clock period. Because of the delays in the path, you cannot capture it instantaneously after it is launched. It takes one clock period for the data to be launched at one edge and captured at another edge on a different flop. The data can change after one clock period, but not before it is captured. Therefore, one clock period is required for this design to safely store the data before it changes. There are also other requirements before a data signal is safely stored in the flop. You must determine whether the data has arrived at the right time and if it satisfied those requirements called setup and hold. We will talk about setup and hold later. When you have multiple clocks in the design and you have data transferring from one clock to another, the worst-case launch and capture edges are not intuitive. So, you'll need to follow certain steps to determine the worst-case data transfer. First, you need to determine the least common multiple of these clock periods. In the example shown, the clock periods are 4 and 6, and they have a least common multiple (LCM) of 12. Next, you align the leading edges. The leading edges of both the clocks are aligned. Next, you unroll the clock until the leading edges of both the clocks meet. The LCM would be where the leading edges align again. In this example, as shown in yellow, the leading edges align at 0 and again at 12. The entire waveforms would repeat itself in the same pattern, with the leading edges aligning again and again after every 12 units. It is easier to locate all the different launch and capture edges when aligned as such. Every transfer pattern can be replicated here, because the entire waveforms would repeat itself. Finally, you determine the worst-case transfer by locating the most restrictive launch and capture edges in the unrolled waveforms. So now you can locate all the data transfers that can happen between the two clocks and find the most restrictive or the worst-case scenario. Let's look at an example with multiple clocks. If you have clocks with periods of 3 for clock 1 and 4 for clock 2. The LCM of the clock periods is 12. First, align the leading edges of the clocks at 0. Since both are positive clocks, we align the rising edges, which also happen to be the leading edges, at 0. Then we unroll the clocks up to 12 units. Next, look at all the edges and identify all the clock 2 falling launch to clock 1 rising capture transfers. Notice clock 2 falling edges at 2, 6, and 10. Notice clock 1 rising edges at 0, 3, 6, 9, and 12. For setup checks, which we will talk about in detail later, you'll have to identify the next closest capture edge. For 2, it would be 3. For 6 it would be 6 or 9. For 10 it would be at 12. Then, identify the worst-case scenario amongst them. You may be tempted to say clock 2 falling at 6 to clock 1 rising at 6. But, since it doesn't account for data delays, you can ignore that one. You can then say the next worst-case scenario is clock 2 falling at 2 and clock 1 rising at 3. The worst-case scenario and the corresponding launch and capture edges are shown in the graphic. Try this activity to improve your understanding.